So, is it okay? Well, so my presentation is going to be very boring. So let's have fun first, and then we will go into boring things. So, and this is the most fascinating slide of my presentation. So, you know, when you read the Bible and Genesis, first line, you are on earth and for the creation of the world. And there is not really nothing. There is something you don't know really what it is, some kind of a span. And you know, why is it the most fascinating slide of my presentation? Because there are two words which can characterize it. The first one is nothing can be distinguished, indistinguishability. You know, you don't see anything. And the second one is the point of view. You are on earth. Okay? So everybody knows the story. The Lord said, let there be light. And the light was, and then you can distinguish. Okay? So now let's make a step in time. And let's look at the beginning of humankind. And in the beginning of humankind, there was the cave. Okay? So this is not really consistent with the Bible in the beginning. So if there is a theoretical question, I think about Peter. So Peter, please don't ask for consistency with this. I will have some difficulty in answering. Okay, so so there was a cave, and as all thermodynamicists know, the cave is cold, about 14 degrees, with small variation over the seasons. And so man was already looking for excess heat, you know, because it was cold, and he found wood, and out of wood he made fire, and it was excess heat. Okay, so just look at this picture. This picture is very important, because what was the problem of the caveman with fire? It was ignition. Okay, so he had already problems of reproducibility. You know, you bang stones, or you use friction of different kind of woods. So maybe because at that time they didn't really try to trigger ignition. Once they had ignition, they blew on it and tried to get the reaction longer. So maybe this is what Jean-Paul could do with Lenner, you know, just blow on it and all right. And other trials were made over the centuries to get heat out of wood, and sometimes it was non-conventional, okay, and sometimes it was pretty hot. Okay, so and there were alternative attempts over time, which you all know, and a breakthrough occurred on wood during the Second World War. This one. Okay, and sometimes it was very hot, and there was some replication which were attempted. Okay. And we tried ourselves with Jenny, because this is common presentation with Jenny. We tried to make ourselves it hot, and we made it hot, okay? But, and now I'm turning to Dewey, and Dewey we had some problem, because you know, no kind of global bake could bring us to industrial heat. Okay, so, and we need, so, we come to a new breakthrough in wood, which is 21st century wood. And so I'm going to take it out of my backpack because I forgot it. So I'm going to pass you this. What you see on the picture is called a anagyro. Anagyro is something which moves. When you want to make it turn in one sense, it turns well. And when you want to make it turn in the other one, it doesn't. So here it works, and here it doesn't work.
The surface is not.
I'm going to pass it. Don't try to make it too strongly, because otherwise it's low energy, you know. So if it's too big, it will not work. So now I'm going into the boring stuff. Okay. So Pierre Curie's theorem. You know, basically, what does he say? In 1894, so a long time ago, in a physical system, if there is a symmetry, nothing happens. You need some dissymmetry for events to occur. Okay? And we announced at SSICCF20 examen that symmetry means disorder while dissymmetry means order, which is a bit anti-intuitive, counterintuitive, because when you see a symmetric figure, generally you think that there is order. And Curie's theorem basically says that we move from disorder, dissymmetry, to order, and so it would contradict the second principle of thermodynamics. So this is where the problem is. And we are going to prove that, in fact, the symmetry means total disorder. So let's consider E, any set of points in a geometric space. What I mean geometric means with a distance, basically. And let us call the symmetric group of G, which is the group of isometries. And then we shall say that E is symmetric as a figure if there exists a non-trivial subgroup of O of G, which we call O prime of G, such that all isometries in O prime of G verify F of E equals E, so invariance through the isometries. So some remark, if the isometry is positive, this means that isotropy and homogeneity of the universe we're considering. If the isometry is negative, it means independence of the orientation, which is a rare property in physics. Just remember the violation of parity, which was proved in 1956. Okay, and the guys who wanted to carry out the experiment were more or less prevented by Heisenberg himself, because he didn't believe it was worth, because parity had to be, and it was not. And because the magnetic field is a pseudo-vector, we cannot have the latter, I mean independence of orientation, just because magnetic field is a pseudo-vector. Okay, it's not a vector. Now, the distinguishability principle, let us consider we're in G. We would want to distinguish point in space, okay? For this, we must not alter the space. So we are obliged to use isometries, because if we don't, if we use, for example, homothetic transformations, homothetic transformation modifies the structure of space, okay? So we use only isometries, and we are speaking about intrinsic distinguishing of points in the space, okay? So this is the reason why we need to use this mean only. This means only to distinguish. Okay, so the definition: two sets E and F are indistinguishable if whatever any arbitrary order on E, so which we call less than, for example, there exists a non-trivial group of isometries of G, such that for all the isometries in this group we have, of course, the invariance, but also the equality of the ordered sets, which is quite important. So just please notice that if for a given point P in E, we consider the set of all distances between P and M, okay, with M in E, then when we apply an isometry to the set, we have exactly D prime equals D as an ordered set. Okay, so it means this is indistinguishable, and if this is indistinguishable, we have this property, and if a set is symmetric, it will be indistinguishable on a subset of isometries. So now I'm referring to modern cryptography. We know, along the centuries and the millenaries, we had a lot of work on what is randomness. What does it mean that something is random or not? And we found, I would say, a kind of a new concept of this in 1983. A guy from Princeton who said that finally, if you have some computation power and you take a set, if you can distinguish elements in it, then it means that there is some order and this is not random. If you cannot, if it's indistinguishable, you have total disorder. So very strangely, it means that depending on your computation power, you can distinguish or not, and you have randomness or not. Okay, this is a relative notion. This is not an absolute one. So now, can we find sets which are indistinguishable in absolute, whatever the computation power? The answer is yes, but it's a bit tricky. I cannot show you here, but it can be proved. It's not that difficult, but okay. So please notice that the notion of order for us here is relative to the isometries and the subgroup of isometries we are considering, which is important. Now, what is a point of view? You know, in physics there are point of views. This is the reason why I told you the most fascinating picture was the first one, because we are on Earth, so we have a point of view on our universe. And this, in mathematics, generally is not considered, and should be, because in physics, the point of view of the observer is important. And so, if you take a set of points of G, the geometric space, and you take any point in G, not necessarily E, we say that E is symmetric viewed from P. Okay? If there exists a non-trivial subgroup of isometries of G, such that for each isometry of the subgroup, we have invariance of the global set P union E. Okay? And with what we said earlier, this implies that we have maximum disorder in P union E if we have this invariance property because of the indistinguishability property. So here is a theorem which is easy to show, to prove. Any symmetric set viewed from any inside point has maximum disorder because of the indistinguishability property and the cryptographic point of view. And what about the square viewed from the outside? And here you have this, you know, you have a beautiful square. You take this, the axis of symmetry here along the diagonal. Say that initially the point P is the red one. And if you use this orthogonal symmetry through the diagonal, then you get the yellow point. And so you don't have invariance. So it means that there is order viewed from the outside. Whereas the square viewed from the inside is total disorder. Okay, so here you have an order. So for physical reactions, it's important because it depends if you have the reaction from the outside or from the inside. It does change completely. Another theorem. Whatever the dimension of G, a sphere is always symmetric viewed from the outside. Because of this very property, you have the sphere, you have any axis going through the point and the center of the sphere, and you have a symmetry. So spheric is always symmetric, and it means that in a true, perfect sphere, nothing can happen, really. Okay? Another theorem. Let us consider any set of points, at least two, such that E is not a sphere and has in its group of invariants at least one reflection, then E is dissymmetric views from the outside. So this, what basically says this theorem is that as soon as you have a symmetric figure but not a sphere, it is dissymmetric from the outside and you have some order. So, can we have the contrary? Because I spoke about symmetric from the inside, dissymmetric from the outside. And here you have typically a figure, so made of three components. If you place yourself in the center, it's obviously symmetric. So symmetric from the outside because the center is not in the figure. The figure is made of these three sub-figures. And any of these figures is not symmetric, obviously. Okay, so you are symmetric from the outside, dissymmetric from the inside. And you can have all combinations, basically. Now, application to physics, because this was math until now. So, and if I apply Curie's theorem, a system is going to evolve from dissymmetry to symmetry. This is consistent with thermodynamics, as I told you. Okay? Every time there is any phenomenon, gravitation, electromagnetic force, and so on, this means that there is a dissymmetry, because something happens. Dissymmetry in our model is the only source of events. So I'm building physics based on this only principle, and I'm expecting in the end, we are expecting in the end to find all the laws of physics force proportional to the mass and acceleration, special relativity, general relativity, quantum physics, everything, okay, with one only principle. Symmetry is synonymous of stability, as Curie said, and as a consequence, a particle, say an electron, must be symmetric viewed from the inside because it's stable. And it is dissymmetric from the outside because it displays a Coulomb force, for example. Okay? And it must have, as a consequence, it must have some components. It cannot be a point like in quantum physics. Because a point is symmetric by itself. Okay? So, some more considerations. Our universe is stable, hence must be symmetric from the inside. If it is stable, okay, which we believe, it could evolve, the case being, from a dissymmetric state to a symmetric one, if there is an evolution, which we don't really know. We think yes, but not sure. The underlying order within our universe is linked, say, to the elementary particles, which it consists in, together with the fields. Don't forget the fields. They are very important. And in my next talk tomorrow, I will speak more about fields. This means that the entities constituting the elementary particles, or even the points in space creating the fields, must be dissymmetric viewed from the outside, and while being symmetric viewed from the inside, because this is stable. And philosophically, this means that the source of order in our universe comes from islands of total disorder. Okay, and they create the global order we see. Philosophically, it's interesting. I don't know if it's true, I hope. But, you know, and another consequence, as I told you before, particles must have components, because if they are only one point, it's symmetric, so they cannot display any property, physical property with this principle. Let's take an isolated system, which is characterized by its Hamiltonian. This equation defines a hypersurface in the space of phases. And if the hypersurface is symmetric, then we have maximum disorder in it, according to what I said, because I spoke about the geometric space in general. To this maximum disorder by Shannon's information theory, we cannot match any information in the true world. Otherwise, there would be a distinguishing process, okay, which doesn't exist because we are symmetric. This means that a symmetric hypersurface corresponds to a state of maximal entropy in physics. I don't think such kind of result has ever been produced until now, and it would be nice to check if it's verified, okay? The least action principle. As a basics, we go from dissymmetry towards symmetry, as I said, and however, when there is a split, say a neutron into an electron, plus a proton, forget the antineutrino, the least action principle we propose is a conservation of what we call the degree of symmetry, without really defining it, because it's an ongoing process and it's a bit tricky. The neutron, for example, is known to be unstable, which we're not sure of it, but let's say it's unstable. And now, at the very moment it splits, the couple of electron plus proton is dissymmetric, viewed from the outside, obviously. And we say in some way that there must be some continuity in the symmetrization process of the system, like in quasi-static transformation in thermodynamics. Okay? So the achievement of physical symmetry is reached through distance. Why? Because when the distance grows to infinite, you tend to symmetric figure. Obvious. However, how can it be, since we have based our notion of symmetry on the notion of isometry? There could be some kind of, thing which would be strange. So it is pretty obvious that we tend to symmetry, so as I told you, when the distances tend to infinite, and this therefore suggests that the symmetry degree law is varying in 1 over r to the alpha positive. So we find, in some way, all the forces we know today, which are in 1 over r squared, or over r to the 7, or to the 5, and so on. And the problem is how to deal with the case when r goes to 0, goes down to 0, because this goes to infinite. And if we had a dissymmetry degree, can it be infinite, in fact? Okay? If we come back to the neutron decay, then this would mean that the internal degree of dissymmetry within the neutron is infinite in some way. First of all, it is known that the neutron must have components because of its internal distribution of charge, as you all know, and has been published. Okay, and here you have the distribution. So let's just remember that the mass and charge are extensive magnitudes, so they can be added up. And if we consider any sequence of subsets of the neutron volume, for example, decreasing to 0, then we must converge towards 0 as a volume, but we do not converge and we cannot converge into vacuum according to Einstein's general relativity of theory of relativity. Theory of general relativity, I'm sorry. Ooh. But to a point where there is a field, because remember, Einstein said that where there is no field, there is no space, which is a very, very important statement. So this means that the limit of the sequence of volumes cannot be 0 physically. And this is where there is a kind of a breakthrough. You have this sequence going down to 0 in the real numbers, but if we consider the serial numbers, we have numbers like 1 over omega, where omega is the first transfinite ordinal of Cantor. And if you have such a volume, say a sphere of radius 1 over omega, at our scale, it's considered as 0, and we cannot see it. It's a point for us. But it's a material point, maybe in some kind of sense of classical physics. There is a volume which is not empty, and it can be filled in with an infinite number of infinitesimal scale particles, okay? And this is the reason why we have a field in every place of the universe. Okay, so we have a subscale to ours, which we cannot reach, but does exist. And if there are enough particles in it, it has an effect at our scale. Because if you multiply omega times 1 over omega, you get 1 and you get a real number. So you have an effect at our scale. This is the model we propose. And this brings to non-Archimedean geometry, which is much more general than the serial numbers even. And this allows to deal very easily and in a good sense, in a good way, with infinite disymmetry degree. Okay. So, what about attraction? So the preceding model was for the split of the neutron into an electron and a proton, basically. So we have the problem with attraction, because when you have gravitation, you know, the equilibrium state is when the two bodies are touching each other. So we keep, in fact, the degree like that, which goes to infinite when the radius goes to 0. And what we say here is that when the two bodies stick together, there are some other forces and some other phenomena at stake. And this is not only gravitation. This is not only gravitation which is at stake. So the symmetry is much bigger than that. And we must deal with other things. Okay, so not only the gravitational field. Okay, and so this is the reason why it works differently. But so we stay and we stick with this formula, which is consistent with what happens. Okay. Now, we were working until now to remain a bit simple in 3D space. If we want to take time into consideration, we have 4D space, adding time, and we have exactly the same thing with symmetries and dissymmetries in the space-time universe. So what does it mean? If you have a symmetric figure in space-time, generally it means motion. You need to have motion to ensure stability. And this is very interesting because, what does there exist today? A theory of physics which explains why there is motion in our universe. We see motion everywhere. Why? Is it a necessity? In current physics, no. In this one, yes, because if you want to ensure the stability of the universe, you need to have motion. Okay? And motion will ensure stability, and when you want to change this motion, which is equilibrium motion, basically, then you will face some kind of, I would say, counter-reaction, because the system wants to remain symmetric and stable. So you go again, you play against the stability of the universe, and then this is why you have the force proportional to the mass by the acceleration, why you have gravitation, not gravitation, relativity, and so on. All the stuff we know. And and just please notice that at low speed, because of the principle of inertia, rectilinear uniform motion does not perturb stability, but it does, thanks to special relativity at great speeds. And we expect the laws of relativity, special in general, being a consequence of this. And it's not that difficult to prove, in fact. And now this is my last slide. Since we have justified the non-Archimedean character of our space, this implies the right to use the serial numbers, which is interesting because we need to use numbers in some way. And so at least we have a tool which has been only built in 1974, so not so long ago. As a consequence of this, we can prove that all the 4 principles of thermodynamics can be applied in the open system we call our universe. You know that thermodynamics can only be applied to closed systems. And in fact, using serial numbers allows this. And the cherry on the cake is this one. It means that if we deal with serial numbers, we have some places where we could expect a new kind of thermodynamics here, which is represented by this set, okay? And yes, probably there is something which we don't know here. Okay, I think I finished. Yes. Well, thank you for.